Next topic 6.11 power. In average power here ratio of work to total time taken T. So average power P average is equal to W upon T. This is the average power. But here instantaneous power, or in this case, is nearly equal to at a point of time. At a point of time. So here P is equal to dW by dt. Now the work done in this case here. So here displacement of, in this case displacement of dr. So dw is equal to f into dr. So now power P is equal to f dr upon dt. So P is equal to f into v. Okay, P is equal to f into v. Now here in the SI unit of, we know that here in this case work done by, in this case, so power is a scalar quantity. Okay, like that work and force. So now here P is equal to f into v. Here v is instantaneous velocity. Okay, now here dimensional formula for power. Here we know that m1 L2 and m1 L2 and T minus C. Okay, dimensional formula for power m1 L2 and T minus 3. SI unit of the power is called watt. SI unit of power watt. Here 1 watt is equal to joule per second. 1 watt is equal to joule per second, and 1 horsepower is equal to 746 volt. 1 horsepower is equal to 740 volt. Next is 1 kilowatt. Here next is 1 kilo, in this case 1 kilowatt. So now 1 kilowatt, 100 watt into 10 hours. 100 watt into 10 hours, so is equal to 1000 watt. 1000 watt into hour. Okay. Good morning, students. Topic number 6.10, collision. Now here as shown in figure, mass m1 here in first case. Consider two masses m1 and m2. Here mass m1, speed of this m1 is v1I, means initial velocity of this mass object. Second one, object m2 in initial situation rest. Okay, in initially this object not moving. Okay, after collision of these two objects, split a different direction, m1 and m2. This is the final speed of m2 and final speed of m1. Okay, now in the here 6.12.1, elastic collision and inelastic collision, means that in all collision here total linear momentum always conserved. In all momentum, total linear momentum always conserved. Okay, So now next in the case collision after time taken by del t. So first one object in this case del p1 is equal to f12 del p. For second one del p2 is equal to f21 del t. Now here f12 in this case is force here in this case exert on the first particle by second, means the second number m2 mass exert on first one particle on m1. Okay, same for the here f21 1 means m1 mass exert on force m2. Okay, exert on force m2, but here total linear momentum is always conserved, means del p1 plus del p2 is equal to 0. Okay, in all collision case. Okay, in all collision case. Now next, total linear momentum always constant, conserved, always conserved, but here kinetic energy of this object is not always in the conserved before collision and after collision. Okay, kinetic energy is not conserved in this case before collision and after collision. Now here in the first case, the kinetic energy of the system is not necessary conserved. Okay, maybe different kind of reasons. Suppose what this energy convert into another type like heat or sound. Okay, energy convert in another form, heat and sound. So now here initial kinetic energy is not equal to final kinetic energy, but here kinetic energy, final kinetic energy plus sound and some type of energy convert in the another form. Okay, so here in this case elastic collision means suppose here we take one spring, compress this spring and apply external force and remove the external force. So here spring again regain original situation, so this is the total kinetic energy is same, but many different type of materials not regain its original shape or size, not regain shape and size. So here some kind of energy convert into another form, some kind of energy here, kinetic energy convert into another form. In elastic collision before and after kinetic energy is same. Okay, now in the second case on the another hand, before collision kinetic energy is not equal to after collision of kinetic energy. So here this is the collision is called inelastic collision. It is called inelastic collision. Okay, now in 6.12.2 collision in one dimension. Now here in first case a complete elastic collision. Complete elastic collision here, theta 1 is equal to theta 2 is equal to 0, both are moving in the same direction. So angle generated between the theta 1 and theta 2, theta 1 and theta 2 is equal to 0. So now here m1 in first case, m1 vi is equal to m2 plus m1 plus m2 into vi. this is before collision in this situation in initial velocity, and now after collision moving both object in the same direction. So here combination of two object masses m1 plus m2 into final speed. This is the before collision m1 vi. So first one case m2 is in rest situation. Now the second one is after collision m1 plus m2 into final velocity. Okay, now in the case here the loss in the kinetic energy on the collision. Now so del k is equal to 1 by 2 m1 v1 I square minus this one before collision in the situation of the kinetic energy minus after collision 1 by 2 m1 plus m2 vf square final speed. So in this case, this is the after collision of the portion, this is the before collision of the portion kinetic energy. Now next is equal to 1 by 2 m1 v1 square minus 1 by 2 in this case m1 square upon m1 plus m2 into v1 I square from equation number this one put here, or in this case this one. Okay, so now here this value put in the case, so equation here m1 and in this case. So now the solve this equation. Now next step is equal to common of in 1 by 2 m1 v1 square, common value 1 by 2 m1 v1 square in this case 1 minus m1 upon m1 plus m2. So now is equal to final is 1 by 2 in this case m1 into m2, 1 by 2 m1 into m2 upon m1 plus m2 v1i square which is positive quantity as axis. Okay, so now this one is only one dimensional and complete elastic collision. Okay, in first case complete elastic collision.